All right, let's talk a little bit about what happens with buffer solutions if you add small amounts of acid or base. First, we'll consider a buffer solution where nothing's been added, and then we'll look at how it changes when I add 0.02 moles of gaseous HCl, and we'll leave the volume at 1 liter of that buffer solution, and we'll assume no volume change. And then similarly, we'll add 0.02 moles of sodium hydroxide to a fresh sample of the same buffer, again 1 liter, and we'll see what the changes are. So let's go to the paper and see what we got. So I've copied a lot of this over. We've used this base a couple of times, so we know the pKb for this particular base is 4.74, where Ka is 1.8, 10% to the negative fifth. We'll focus on this in a minute, but let's get the pH of the existing buffer first so we can see how much it changes. So the pH, or in our case, since we got a base, the pOH is equal to the pKb plus the log of the concentration of our ammonium ion over the concentration of the ammonia. So that'll be 4.74 plus the log of 0.250 divided by 0.100. And then you're going to plug and chug, very similar to what we've done before. 4.74 plus the log base 10. Make sure you're doing log base 10 and not log base E, which is our ln, or natural log. And we get a pOH of 5.13. So our pH of our resulting solution will be 14 minus 5.13. And so that'll be 8.86. So that's the initial buffer before I do any addition. So this is the original. Now, here we're going to add our 0.020 moles of HCl. So this is situation 1. We're going to need to take a little look at what's going on. So we got our ammonia versus our ammonium. So we got 0.250 molar, 0.10 molar. And since it's 1 liter, we're going to assume that those are moles since we got 1 liter of total solution. If we add acid, that's going to convert ammonia to ammonium. So it's going to be minus 0.020, or it's going to be 0.080 moles left. We're going to say plus 0.020 moles here, or 0.270 moles. This assumes the volume doesn't change. If it does, you're going to have to consider that dilution effect. You can still calculate the moles and subtract, but then you would have to divide through by the total volume. But then we pretty much do the same thing we did above. pOH equals pKb plus log of ammonium divided by ammonia, or 4.74. And what's going to be different is going to be 0.270 up here and 0.080 down there. So it's going to change, but not a whole lot. And so we run that through our calculator. And we get a pOH of 5.26. Calculating the pH from the pOH, 14 minus 5.26. We get a pH of 8.73. So we can see it went up or went down a little bit when it added the acid, but not a whole lot. Situation 2, we're going to add 0.020 moles of sodium hydroxide. And so you're going to get very much the same type of deal that we had in the last one, with one notable exception. It's going the other way. So adding a base is going to consume ammonium and produce ammonia. So 0.020 moles. So that's going to be 0.120 moles. But this will be minus 0.020 moles, or 0.230 moles. And so then we're going to use our Henderson-Hasselbalch again. And so we'll have 4.74 plus log of 0.230 divided by 0.120. The pH will go up, but not as much as you might think in an unbuffered solution. And so our pOH is 5.02. And so our pH for that buffer is going to be 14 minus 5.02. And so it'll be 8.98. And so you can see it went up a little bit, but not a lot. So looking at the summary, you can see the original pH of the buffer. We did one more decimal place on our work, but 8.9. If I had base, it goes up just a little bit, more or less a tenth, to about a pH of 9. With HCl, it goes down about a tenth to 8.8. But notice that it only varies slightly in each case and doesn't change as much as you might think that it would. And that's the whole point of the buffer.